Hello everyone, welcome to my booth. My name is Hossein Rafa and I would like to present my work with Erini Gudeli and Reza Kholgi on predicting the sintering rate of nickel nanoparticles using molecular dynamics. Nickel nanoparticles are widely used in batteries, catalysts, and filters. Properties of nickel nanoparticles strongly depend on the size of particles. During the production of nickel nanoparticle by gas-phase synthesis in a flow reactor, primary particles collide with each other and stick together due to the potential forces between the particles. The growth rate of nickel nanoparticles during the sintering is determined by a parameter known as the characteristic sintering time or TIS, which is defined as the time required for the reduction of the total surface area uh, by 87% of the initial surface area. As the snapshots of coalescent particles show, the concave region around the center neck is gradually filled by mass transfer mechanism on the surface and inside of the particles. The primary goal of this study is to obtain an accurate characteristic sintering time for nickel nanoparticles using molecular dynamics. Using molecular dynamics, the evolution of the normalized surface area of two freestanding nickel nanoparticles with a primary particle diameter of 2, 3, 4, and 5 nanometers at 1200 Kelvin are shown. Based on the molecular dynamics simulation, a general formula for the characteristic sintering time for nickel nanoparticles is proposed as a function of temperature and the size of the nanoparticles. It was found that the sintering rate is highly dependent on the size of particles. In other words, smaller particles result in a faster sintering. The reason relies on the fact that small nickel nanoparticles, typically with a diameter less than 5 nanometer, undergo recrystallization and surface melting during the sintering. Using molecular dynamics, the crystallinity and surface melting of nickel nanoparticles are investigated. MD-derived X-ray diffraction or XRD patterns of coalescent nickel nanoparticles with a size of 2 and 3 nanometer at 1000 and 1300 Kelvin are presented. Also, to show atoms' mobility, cross-sectional snapshot colored according to their local disorder variable. It is worth mentioning that the small values of D less than 1/10 correspond to FCC crystal structure, while large value of D, typically more than 3/10, indicate a glassy or liquid nanoparticle. As the figure shows, during the sintering, surface melting starts from the outermost layers of nickel nanoparticles. So, the nanoparticle melting temperature could be highly dependent on the size of particles. The size dependency of melting temperature of nickel nanoparticle is investigated by calculating the average interatomic potential energy. The MD-derived melting temperature are compared with empirical models shown in green and red solid line, also available experimental data, the blue diamonds, and MD simulation results, the pink circles. The results are in a very good agreement with the literature. As we can see, by increasing the size of particle, the melting temperature increases and gradually reaches a plateau corresponding to the melting temperature of bulk nickel. From previous slides, we found that nickel nanoparticles undergo phase transition during the sintering. Here, the results of characteristic sintering time of nickel nanoparticles are predicted by phenomenological models for solid states sintering. the blue and red lines, as well as viscous flow sintering, the dashed line, and also the MD simulation and the proposed equation based on the MD simulation. As you can see, for nanoparticles with a diameter of 3 nanometer, at temperatures below 1100 Kelvin, particles are fully solid. The results from MD simulation and the proposed equation nicely reproduce the results obtained from phenomenological models. As temperature increases, the MD-derived characteristic sintering time deviates from the literature. This implies that the surface melting has started. Finally, at high temperatures above 1400 Kelvin, we can see that particles are fully melted. Finally, we can see the values for temperatures more than 400 Kelvin reaches the value, asymptotic value corresponding to the viscous flow sintering. So we can see a very good agreement between the MD simulation as well as the phenomenological model. Finally, the performance of the MD-derived characteristic sintering time is benchmarked by predicting the morphology of nickel agglomerate in a flow reactor after 7 seconds of sintering. The result of the mobility and primary particle diameter of nickel agglomerate in a reactor are measured by transmission electron microscopy or TEM measurement, and then compared by the value predicted by molecular dynamics simulations. The results of this study are in a very good agreement with the TEM measurements. The model shows that the average mobility diameter of agglomerate is rather constant up to around 500 Kelvin and steeply decreases to 35 nanometer at temperatures as we increase the temperatures. For about 773 Kelvin, the agglomerates sinter into compact spherical structure and their mobility diameter asymptotically decreases to 32 nanometer, implying that nanoparticles are fully sintered. So we can see the spherical structure of nickel agglomerates. Thank you for your attention and for your time, and please feel free to ask if you have any question. Also, we can chat if you like, and I can explain more about my project. Thanks again.